Hello friends and welcome back. In this video we'll be talking about torque, a new new physical quantity of great importance and plenty of applications. Torque is typically denoted with the letter tau, the Greek letter tau, and torque is a vector defined as the cross product. Go and watch the video if you don't know what that means, of r, the position vector, or in this case, well, I'll mention now what this is. There's a special nomenclature that's typically used, and the force. So take this situation. You have the origin of your reference frame. You have a point P, and you have a force applied to this point P. All right. As usual, what we can do is we divide, well, first of all, let me call this is R, the position vector. In this context, R is also called the lever arm vector. Okay. O is also called the lever fulcrum. It means the pivot, basically. So the pivot about which we want to calculate the torque. And as usual, I forgot to finish this. We can decompose the force in its parallel and perpendicular component to the to R. Okay. And what else? Yes, so this is F perpendicular, this is F parallel. If you remember the properties of torque, this is, so the magnitude of the torque vector is precisely the magnitude of the lever arm, so the length of the lever arm, the magnitude of the force F, and the sine of the angle between them, where this is the angle between them. Or in other words, it's R times F perpendicular. So this is already, you may remember or have noticed about the cross product that two vectors that are perpendicular maximize the cross product, whereas two vectors that are parallel have a zero cross product. And this is precisely emphasized here, where if you apply a force at a certain point with a separation r from the origin about which you're calculating the torque, then only the perpendicular component, or the tangential, if you want, component to that force contributes to a torque. Torque, if you know the torsion or in English, you know that means something that induces rotation, a twisting. And in fact, this is precisely the physical meaning of torque. We will talk about it in more detail next week. But it has a similar role in rotational physics as force has in linear physics. But more on that next week. For now, so this is a definition. The magnitude, as we said, it's the product of the lever arm length, the magnitude of the perpendicular component of the force. The direction is, as usual, using the right-hand rule. So in this specific example, the direction would be coming towards you, perpendicular to the page. But for now, this week at least, we won't be worrying too much about the vector nature of torque, but we will be focusing on what having, well, a certain magnitude of a torque implies when we do equilibrium physics or statics. Okay, Now, what about the units that torque is measured in? Well, it's the units of length times the units of a force. So if we're talking about SI units, this would be meter times Newton, which we're more used to seeing as Newton times meter, and we used to call this joule. It's the same for energy, okay? However, there's a big caveat, which is because it can be confusing to use. It wouldn't be incorrect formally, but because it would be very confusing to express a certain value in joules when we mean that that's a torque, because torque is inherently a vector, is a vector quantity, and it's a vector that precisely has the physical nature of a force applied at a certain displacement away. Whereas if I tell you, oh, this quantity is 100 joules, you would imply that that's an energy. And energy is, first of all, not a vector, it's a scalar. And it can have completely different physical nature than a force times a displacement. It could be mv squared, for example, a mass times a velocity squared, like kinetic energy. Okay, so when we speak about torque, we always want to use Newton times meter as your unit. Truth be told, if you tell me that this is kilograms meters squared over second squared, I could not fault you. And in a way similar, if you use joules, I couldn't actually, mark you down. But it's really, in the interest of clarity, we want to be using Newton times meter as much as possible. All right. We can make a quick example to see where we're at. Calculate a torque or two. Let's do this. Take, for instance, that's an example that's close to home. Let's take the Leaning Tower of Pisa. Okay, that's a big tower of mass m that is currently at an angle, leaning of an angle theta. This is the center of mass. Formerly the center of gravity. Maybe that's for a future video. And we can ask, what is the torque that gravity is applying on the tower? Now, there's already a problem in this question, which is, in order to calculate a torque, you need a force, and that we do have, because the force of gravity is pointing down and it's mg. And you need to specify what point you want to calculate the torque about. We need a lever fulcrum. In this case, I'm going to idealize the leaning tower as, a skinny rod, and this is my origin. So whenever anybody asks you, what is the torque, blah, 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 they need to tell you of which force, the torque of this force, the force of gravity, and about what point. And this is fundamental. Simply because calculating the torque about different points would give you different results, and it would have a different physical meaning. So it's important to specify the point. Well, in this case, it's pretty straightforward to calculate that the torque is equal to the vector r, which in this case is the vector joining the lever arm. So this is the vector r. And then cross the weight of the Leaning Tower of Pisa, which is W. So this would be something like the magnitude of R, which is 1/2 of the height of the tower, times the weight of the tower times the sine, so I'm calculating the magnitude now, times the sine of the angle between the two vectors. The angle between the two vectors, be very, very careful because it's this one, okay? In order to measure the angle between the two vectors, we need to imagine that they both start at the same point. So this is R and this is force. Okay, so this here is the angle theta. I know that you're tempted to say that this is theta, but that would be tricky. That would be risky. In this specific case, it would give you the same result because, well, the sine of 180 minus theta is the same sine of theta. But I'd like to give you rules that you can utilize consistently, and so let me delete this. This is the right theta. By the way, if you remember, then the torque in this case is, if you take R and you apply the right-hand rule from R to F, your thumb is pointing into the page, so that would be perpendicular to your screen into the screen right now. So sine of theta. Okay, now I'm going to go on Wikipedia and look up some numbers. Let's find out. Okay, so Wikipedia claims that this angle is roughly 4 degrees, okay, 3.99 or 3.97, whatever. That this mass is roughly 14,500 tons, so that's times 10 to the 3 kilograms. So that would be 1.45. Let's do 1.5 times 10 to the 3, 4, 5, 6, 7. All right, times 7. Yes. 1.5 times 10 to the 7 kilograms. And the height is 57 meters. Great. So plugging it into my trusty calculator, we found that the magnitude is roughly, this is 2.98, all right, so something like 3 times 10 to the 7 Newton times meter. Nice, interesting. And direction, right-hand rule pointing into the page. Wonderful. All right, I think this was it for torque. Thank you for watching, and I'll see you soon.